Hello students, in this video I will go through discussing other properties involving logarithms. So up to this point we've worked with various types of problems involving logarithms, and we've utilized and capitalized on the following identities: that the conversion going from an exponential equation to a logarithmic form can be converted in this manner, and it can go either from left to right or right to left. This identity will prove to be important later on as we go through and solve more complex problems or needing to prove certain other identities in the future. That log base of a is equal to 1, and the reason for this is a to the first is equal to a. And consequently, we can say log of 10 is also 1. If the base of a logarithm is not explicitly stated, that's by default 10. So 10 to the first is equal to 10. Log base a of 1 is equal to 0, and that is consequently because a to the 0th is equal to 1. And actually, log of any base, of 1 will always equal to 0. So for log base 10 of 1, that is also equal to 0. Log base a of 0 is undefined because this is not possible. We cannot take a base of any number, raise it by another number to attain 0. So because of this, there's no solution. We cannot take the logarithm of 0. This is not possible. And as a matter of fact, we cannot take the logarithm of any negative number as well. Now, in order for us to solve more complex problems, or for us to even be able to solve this problem that we started this whole discussion on, it will require us to, again, learn more properties. Again, from that one problem sprung up so many different things, so many different paths for us to study, right? We studied exponential equations, and then from exponential equations to logarithmic equations, and we're still investigating, and yet we still haven't fully acquired all the different tools yet to be able to answer this question. But we'll get there, okay? After this lesson, this is just one step closer to getting to that point. All right, so in our pursuit to discover more properties and more laws associated with logarithms, let's just recall some properties involving inverses. So if f of x and f inverse of x, are both inverses of one another, then the following must be true. And this was discussed back in a unit involving functions where I had shown you guys the existence of an inverse function, and this is and this right here is a way for us to test whether or not two functions are inverses of one another. There's more to this than just being a test. This is actually one of the properties that we can capitalize on. And how are we going to do that? Well, suppose g of x is equal to 10 to the x, and g inverse of x is log of x, which we now know to be the case, that the log of x is the inverse of 10 to the x. Then the following must be true. You take g, and wherever you see x, you replace it with log of x, and hence we will end up with 10 to the power of log x. Based on this property here, this power must evaluate to x. As cryptic and as abstract as this expression may be, this will evaluate to x because of the very nature of inverses. And conversely, right, going the other way, we can also take log of 10 to the x, and this, again, as abstract as it may appear, it too will equal to x. And these two ideas are the main ideas that we are going to be capitalizing on. And these ideas are going to spring up in the next 3 derivations that I'm going to do in this video. All right, so we recognize these to be the identities. We recognize from the previous slides those identities. What happens, okay, in the case where I have a power being expressed inside of a logarithm that has a different base? So right now, this is base 10, right? And inside of the logarithm, that's base A. So they're obviously different bases. Is there a relationship that we can form involving A and B, perhaps? Is there a different way that we can re-express this expression? So that's what we're going to try to do in the next like 30 seconds. All right. So what are we to do? This is one of the tricks, if you want to call it a trick, in algebra. When we don't know something, it's usually good to try and re-express it in other forms. So when I say it, okay, I'm looking at this, I really see that there is 2 parts here. I see here that I have a power, okay, of base A. So therefore, I want to call m is equal to log of A. And by doing so, I can convert this in exponential form and write 10 to the m is equal to A. I can then re-express what I started off with in terms of m. So why am I doing this? Well, that's because I want to capitalize on this idea, right? Remember, this was one of the identities of the inverse. Log of 10 to the x will give me x. Log of 10 to the u will give me u, and so on and so forth. Remember this, okay, as we go through the next couple steps. All right, so the next thing we're going to do is I'm going to apply the power rule for exponents, and I can see that the exponents gets multiplied by one another, and look what we have now. 10 to the bm, right? Wait a minute. Log of 10 to the x is equal to x. Log of 10 to the u is equal to u. Log of 10 to the bm, what would that equal to? It must equal to bm. So what happens from here? Well, I know what m is. M is equal to log of A, isn't it? So I can re-express this. So b times m is really b times log A. This here, ladies and gentlemen, is the power rule for logarithms. So what it really states is if you have a power expression inside of a logarithm, the exponent can come out in front and become a coefficient. This will prove to be super useful later on. So this is, again, the power rule. The exponent simply comes out in front and it becomes a coefficient. All right, so what happens if the argument inside of the logarithm is a product? Again, I am going to try to come up with a relationship between A and B, and to do that, I will need to re-express this somehow. So what I'm going to do is I'm going to call log of A equal to m, and I'm going to call log of B, log of A is equal to m, and then I can say 10 to the m is equal to A. And I can say log of B is equal to n, so I can say, that should say a b there. How embarrassing. So then I can say 10 to the n is equal to b. So now that I know this, okay, I can then re-express log of AB as 10 to the m times 10 to the a. Log of 10 to the m times 10 to the a. And here I can apply the product rule for exponents. So the product rule for exponents says, because if I have the same base, I can add the exponents. And that's exactly what I'm going to do. I'm going to add the exponents together. So I have now log base 10 of m plus n. Wait a minute. Isn't this a power inside of a logarithm? Wait a minute. I can now apply the power rule, can I? So that coefficient can come out in front. So now I have m plus n times log of 10. But wait a minute. What was log of 10 again? Oh yeah, that was one of those identities, right? Log without an explicit base stated is base 10. So log of 10 is equal to 1 because 10 to the 1 is equal to 10. So really, this all reduces down to just m plus n. And what is m plus n? M plus n is log of a plus log of b. This is the power rule, ladies and gentlemen. If you have a product inside of a logarithm, this then becomes the sum of those logs. Again, the logarithm of a product becomes the sum of the individual logs of the sum of the individual parts. All right, so we just covered the quotient, the power rule and the product rule. Now we're going to take a look at the quotient rule. So suppose I have log of a quotient. Again, I'm going to do something very similar. I'm going to call m is equal to log of a and n is equal to log of b. And with this, I want to convert this into 10 to the m is equal to a and 10 to the n is equal to b. Very similar. And with that, I am going to re-express the quotient not as a and b, but rather as m and n. And because I have a quotient now, and inside I have a power of 10 to the m and 10 to the n, and they're the same base, I can then simply apply the quotient rule for exponents, therefore subtracting the exponents because I have the same base. And I can now apply the power rule. M minus n, the exponent, comes out in front, becoming a coefficient. And recognizing log of 10 is equal to 1, this whole becomes just m minus n. Therefore, the quotient, log of a quotient, becomes log of the numerator minus log of the denominator. All right, so we covered a lot of different properties in this lesson, in this video. Let's just take a look at all the summaries of it, okay? So I started the lesson off going through these properties here, okay? They were utilized in previous videos and previous exercises. I've also talked about these concepts, okay, in previous exercises, but here they are once again. These are the concepts that were covered in this video. So this idea of an inverse, okay, was utilized, and these concepts were capitalized upon. So in conjunction with laws, the properties of exponents, the quotient rule, the product rule, and the power rule, I was then able to come up with product, quotient, and power rule for logarithms as well. So again, I encourage you to refer to this chart. Do not attempt to memorize this chart verbatim, but attempt to memorize it through practice. Because if you create index cards and just memorize it verbatim, you will not understand this. You will not be able to apply this fluently. The only way to get through this is to go through enough exercise and then becoming fluent that way. Okay.